So I've written here kind of detecting the gas exchange threshold, but actually detecting the gas exchange threshold is really about detecting it because we're going to understand the physiologies to support this process. So we're going to use this data set here, and this is the same data set that we're going to use throughout for the rest of this lecture. This is data collected in our laboratory from one of our PhD students. Now, what I've done is I've taken the key parameters that are of interest in relation to gas exchange threshold. So we've got our blood lactate response to incremental exercise. So we get this conventional response that you can see where you get this kind of very normal gradual increase in blood lactate and then a sudden acceleration. So we get this transition from predominantly aerobic to anaerobic metabolism. We've then got in the panel at the bottom, this is the VO2 response, and give or take, aside from this workload here, this is collected with Douglas bags, so there's always some inherent limitations with Douglas bags. But can you see that actually it's pretty linear against exercise intensity? In other words, as we've already alluded to, if you get a linear-like increase in exercise intensity, you get a linear-like increase in ATP turnover rate. That is the ATP needed for the generation of force within the muscle, reflected, because VO2 is basically the reflection of ATP turnover rate in the rise in VO2 recorded at the mouth. If we then look at CO2, now CO2 is quite interesting. Again, don't necessarily be fooled by this one point here, which looks a little bit out of line, but can you see that generally, and I'm going to put some lines on here in a moment to help us, can you see that generally it's quite linear to start with, and then it does seem to inflect, it does seem to support a little bit about what Paul and Rossiter are referring to in their Journal of Physiology paper. And then VE, which is our minute ventilation, which is a function of frequency, and we've already seen that frequency doesn't really rise until we get to that lactate turn point, and tidal volume. So if you multiply frequency by tidal volume, you get a minute ventilation score. And again, you'll notice that the pattern for VE looks almost identical to the pattern of response to minute ventilation. So to support that, this is kind of a nice overview. So as work rate increases, VO2, VCO2 and VE increase linearly up to the point where the lactate appearance exceeds disappearance. So let's mark that on the graph for us. So anything that I've put which is in this kind of yellow is going to be below our lactate turn point, and anything above it, which is going to be in subsequent slides, will be in a green, or a green will be above the lactate turn point. So what I've done to make our work a little bit easy to understand, I've put these lines on to help us. Now it's pure chance that this data point is actually lower than the others. It's not a common occurrence that it's suddenly lower. It's just the way that data collection has gone. But you can see, I don't want to necessarily focus on the VO2 graph, but I want you to focus on these graphs here. Look at the CO2. Can you see, now I've put the trend line in, that you've got a linear-like response up to this point here, which corresponds to the workload at the lactate turn point here. And then you get this acceleration. The same workload that we see for VE. Remember that breathing frequency, as we saw on the previous data set, doesn't show a significant increase. So the only thing that's really driving up minute ventilation up to this point is tidal volume. So we have to ask ourselves, what's driving up breathing frequency, and we'll explain that. And I've done this with the VO2 here, but really the VO2 data is much more linear. It doesn't really show that kind of bend in the data. It's certainly nowhere near as marked as you see in the three other graphs. So let's now see if we can connect this up. So here we go. So remember that in the Paul and Rossiter paper, they said that GET fundamentally reflects an imbalance in the VCO2 to VO2 relationship. That VO2 is proportional to workload, and VCO2 is therefore proportional also to workload. The amount of CO2 you produce is proportional to the amount of energy that's needed to a point. Now what you see is this. At work rates beyond where the rate of lactate appearance exceeds its disappearance, so that is the lactate turn point, okay, which we identified on the previous graph. So I'm just going to flick back so that we're with it. So we identified it at a workload here at 210 watts. So at that point, where the rate of appearance of lactate exceeds the rate of disappearance, CO2 output rises more than O2 uptake. And that is why, again, go back, we suddenly lose the linearity in the CO2. VO2 is rising in a linear-like fashion in proportion to exercise intensity. We've now lost the connection. In other words, CO2 is no longer coupled to O2. O2 is coupled to exercise intensity. CO2 has been coupled to O2. It's got a proportional rate of increase to exercise intensity. It gets to the lactate turn point. It has now lost its coupling, 1 to exercise intensity, but 2 to VO2, because VO2 is increasing linearly, CO2 no longer is. Why? It comes back to what we saw in that slide from Paul and Rossiter and Brooks, which is the CO2 rises more than O2 uptake as CO2 derived from the bicarbonate buffering of lactate is added to that from the metabolic CO2 production. So remember that you're producing lactate, which is in response to the increase in exercise intensity, because you're getting greater recruitment of less efficient type 2 fibers. The less efficient type 2 fibers, the byproduct is that we get lactate. That really isn't a massive problem because we don't produce lactate in high concentrations at low workloads. And the majority of the lactate that we do produce, well, not the majority, but a large amount of that lactate is either converted to pyruvate. Some is, and that's either happening in adjacent cells, so we can move it from cell to cell, muscle cell to muscle cell, or a reasonable amount of it is actually being converted back to glucose in the Cori cycle in the liver. But as the exercise intensity increases and you get a greater reliance on less efficient type 2 fibers, then the amount of lactate we produce consequently increases. But we've got this second source of CO2, so let's see if we can kind of unpick this. So this is what's called the V slope. So VO2 is going up proportionally, but now you get this disproportionate increase in CO2 because of the second source of carbon dioxide. And that second source of carbon dioxide is a result of lactate now coming into contact with bicarbonate. And here's our chemical formula. So what we have here, this is C3H6O3, this is lactate plus bicarbonate. So fundamentally bicarbonate is extracellular, and the lactate is fundamentally predominantly intracellular. So what you've got to remember is that you've got an alkaline here and you've got an acid here. So we move from predominantly an acidic to an alkaline. We create a pH gradient. So the lactate is pulled from the cell. It interacts with the bicarbonate in a reversible reaction. The net result of that is we produce H2CO3, which is carbonic acid. And we get also what is C3H5NO3, which is sodium lactate. So carbonic acid and sodium lactate. Still doesn't explain our second CO2. But if we go a stage further, what we end up with, here we've got our carbonic acid. The carbonic acid interacts with an enzyme, which is carbonic anhydrase, in a reversible reaction. But look at the byproduct. The byproduct is carbon dioxide and water. That is the second source of CO2. Remember, you've got CO2 coming from the metabolic process of the tricarboxylic acid cycle, metabolism. And that CO2, that amount of CO2 that's being produced is proportional, if that's all it was, is proportional to exercise intensity. But because you are now producing lactate, because you've got these less efficient fibers, and because one of the things we're trying to do is we are trying to maintain a stable intra and extracellular pH, the lactate, which is acidic because it's rich in hydrogen ions, it's got these 6 hydrogen ions, we try and neutralize it, and you do that by interacting with the bicarbonate. The byproduct is one, you get sodium lactate, that's pretty benign. 2, you get the carbonic acid. The carbonic acid interacts with the carbonic anhydrase. You get carbon dioxide and water, the second source of CO2. And so you can start to get the picture, which is, well, hold on, I've got a second source of CO2. VO2 is rising proportional to exercise intensity. The second source of CO2 added to the CO2 coming from metabolism explains why at the lactate turn point we get this uncoupling between VO2 and VCO2. Now you might be thinking there and being a smart cookie going, but hold on, in previous sessions you've referred to the fact that really lactate's not an issue and actually we shouldn't be thinking about lactate. Okay, that's a very fair comment. So if we actually deal with this and perhaps make this more applicable and ignore the kind of the lactate part of this and just think about the hydrogen ions, then actually we end up with exactly the same principle. Hydrogen ions will come into contact with the bicarbonate, you'll get the carbonic acid. The net result of that is if the carbonic acid interacts with the carbonic anhydrase, exactly the same principle, H2O and CO2. So although I'm referring to lactate, because we're referring really to the lactate turn point, actually remember that the key parameter here in terms of creating metabolic inefficiencies is the hydrogen ion. So although we in essence get an appearance and disappearance of lactate, it's the hydrogen ion that has the potential to impair metabolic function, has the potential to create the change in the cell pH, has the potential to actually change muscle function. So as much as we kind of talk about this in terms of a lactate-based response, please do remember that fundamentally it's the hydrogen ion that's the bit of interest, and it's exactly the same outcome, the second source of CO2. So now let's see if we can put this together and think about how we identify this point. Well, you can go, well, I can see it here. Here's one point. Well, this is V slope. And in V slope, which was originally developed back in actually in the 80s from Carl Wasserman's lab, a guy in there, the surname of Beaver, worked with Wasserman, and we're able to identify this, which is this disproportionate increase in CO2 to VO2. But it doesn't necessarily help us. It's one way of doing it, but I want to delve in a little bit further to get a little bit clearer on some of the physiology. So we go back to our data set. Now I've dropped the blood lactate profile here because I've added in a new graph, which is this bottom graph here, to help explain what is going on. I've identified for us as before, remember 210 watts, we've already identified based on the blood lactate response is the lactate turn point. And remember that all we're trying to do here is connect our blood lactate physiology and metabolic physiology to our gas exchange physiology to really have a non-invasive way of identifying the aerobic capacity. Now, this is where we connect everything together. Remember what we said earlier on, that when we look at the response for CO2 and we look at the response for VE, remembering that minute ventilation VE is the function of frequency and tidal volume. Notice that the two are proportional. So remember, it gets complicated here. Remember, VO2 rises in a linear fashion because it reflects the ATP turnover rate, so it's proportional to exercise intensity. CO2 rises in proportion to the exercise intensity up to this lactate turn point. CO2 is what drives respiration. So this is really important. I'm sure you're aware of this, but it's not a lack of O2, it's an increase in CO2 that drives respiration. And we can see that it drives respiration because you get a proportional increase in the minute ventilation response, the proportional increase in VE. And remember, in that earlier data set, we were able to identify that predominantly up to the lactate turn point, that increase in VE is due to the increase in tidal volume, not breathing frequency. But now remember that we've said that at the lactate turn point, the reason you get this uncoupling between VO2's linear response to workload and CO2's suddenly non-linear response to workload is the second source of CO2. And this is where we go into the zone of what is called isocapnic buffering. That is, the bicarbonate now interacts with the lactate or the hydrogen ions, and we get this zone. I'm going to add that zone into it in a moment for us to see. But this is where it gets fascinating. Because VE rises in proportion to the increased CO2, VE actually retains a linear relationship with VCO2. So you get this very nice linear response. You see they're absolutely identical. They're going at exactly the same rate against exercise intensity. So, when we go beyond, can you see that fundamentally you get this kind of very, very similar response between VE and VCO2? So this is going beyond the turn point. So how does this connect? Well, we're going to connect this by understanding what are called ventilatory equivalents. Ventilatory equivalent is the minute ventilation divided by the gas exchange parameter, in this case VCO2. We'll also do it for VO2.